So as we've been doing so far, we've been working on the constant velocity particle model. All right, so let's start off with that. So some of this is going to be old hat. And again, if you have your packets out, you can follow, the steps that I'm about to show here, one by one. So on the first page, we have those 4 definitions, things that we can measure. We can measure stuff like distance, we can measure time, we can measure position, we can measure velocity. Some classes classified 4 different things, but those were pretty much the standard. Position, time, distance, velocity were pretty much the standards. And this is abbreviated as CVPM. And then we went into, and then we defined those four items. We listed those 4 items, then we defined them, then we ascribed symbols to them and units to them. Okay, so for example, displacement was one, or displacement or position. And so we defined that. I'm not going to redefine it here, but we gave it the symbol delta x. And we know that if we wanted to find displacement, it would be the final position minus the initial position. And we gave the symbol of displacement or the units of the displacement as the meter. And it could be different types of meters. It could be centimeter, it could be decameter, it could be nanometer, different types of meter, because meter is generally the SI unit of distance. So this was our symbol, this was our unit. And then we went on to find stuff like velocity, which is meters per second, and then acceleration, which we're going to get into, meters per second squared, time, symbol is T, and the symbol for that is S for seconds. Okay. So the whole part of this lab, the thing that we're going to be doing, not only with the CVPM, but for all the other models, the CAPM, the momentum labs that we're going to do, the energy labs, all of the labs that we're going to do is going to be within a construct called claim evidence reasoning, which is basically another way of defining the scientific method. And so I'm going to write this up. Scientific method, because that's basically the standard by which we perform experiments via the scientific method. So we are always going to be doing the scientific method within the claim evidence reasoning dynamic, or the CER. Basically what claim is your hypothesis. I believe something's going to happen. I'm claiming it. Evidence is testing, experiments, organization of data. That's my evidence that supports my claim. Reasoning, interpretation of data via graphs, equations, standard deviation, standard error, and conclusions. Well, without the conclusion, that's evidence is all the other things, tests, organization of data, graphs, etc. And reasoning would be the conclusions. At the end of my experiment, this is what I've found. This is my reason for why I believe it's going to happen. Here's the evidence that supports that claim. And now I'm reasoning it out through analysis or conclusion. So this is what we've done so far. Observation, what did we see? What could we measure? What are the relationships between something like position and time, right? We've already established that they are directly related, where the position is the dependent variable on the y-axis and time is the independent variable. Because position was that variable that we could manipulate, sort of. You know, we saw the car go and we could kind of change the position or look at how the position changes through time. And we're just basically measuring time. So position was the independent variable at y-axis. Time is the independent variable x-axis. So the observation is encapsulated in these questions. What do we see, obviously? And then what can we measure? Those two questions, or just write that one here. The observation generally leads to a hypothesis, or what we call a claim. This is what we're claiming is going to happen. Our reasonable guess, our estimate. And after we establish a claim, we want to go test and see if our claim is true or not. We test it by way of experimentation, by experiments. So tests or experiments is what we generally do next. We collect evidence. The tests of the experiments are the evidence in the lab. Claim evidence. We get all this information, we get all this data, we organize it into a data table. And if you look back on the CVPM, there's that one section, I think on page 2, where it says organize your data. That's where you establish that data table, right? So we got our evidence, and then from the evidence, we went to organize the data. And we generally organize the data in a data table structure. Right? And so that data table for us so far, just the example again, is going to be the position measured in our case, centimeters, but it could be measured in meters. That's a typical SI unit. That's you. Position in centimeters and time in seconds. So we'd have the dependent variable on the left-hand column. This is the y-axis variable, all of these. And this is the independent variable on the x-axis. So in algebra, we would just label y versus x. In physics, we translate those abstract algebraic or mathematical symbols into something real, like position versus time, as opposed to just arbitrary y versus x. And so this was what we've done so far. This is the dependent variable. What we can change, what we can manipulate. We were manipulating position, so to speak. And then time was just occurring, taking place. We don't manipulate times. We just record what's going on in time. So that's our independent variable. And just for the record, time will always be your independent variable. It will always be on the x-axis. Position versus time, velocity versus time, acceleration versus time, force versus displacement, energy versus time, you know, it's off the top of my head. Force versus radius with gravitation, things of that nature. And we organize our data. So that's just an example. We've seen this several times. Next, interpret data. And I need for you to just not only take notes for this, but if you already have it and you just all had, good. This should be refresher, because we've seen this before. But the reason why I'm stressing it is because this dynamic is what we're going to need to employ every time we do a model. Observation, hypothesis, experiments, interpretation of data, analysis, okay, which is conclusion. The scientific method within this so-called NGSS, claim evidence reasoning dynamic. It's another way of saying a wheel is a wheel. My humble opinion. Okay, so interpretation of data. Graphs, I'm going to abbreviate standard deviation by saying STD. And standard error is STE. That's all falls on interpretation of data. All of this falls under evidence. And conclusion statement, okay, what happened? What were some obstacles? Why did your results seem too high? Why is your acceleration due to gravity 11 meters per second squared as opposed to 9.8? I mean, what went wrong or what went right? So that would be the reasoning part. Not only have we described all the elements of the scientific method, but we have identified the parts of the scientific method that are the claim, the evidence, and the reasoning. So this is basically going to be implicitly used or embedded within the scientific method. The scientific method is the standard by all scientists, whether you are a biologist, physicist, chemist, astrophysicist, it doesn't matter. So today, this brings us back to the part of our CVPM. If you have your physical packet, you should be on page 3. We're going to need a little bit of space to do our standard deviation. Okay, standard deviation. And then, as we've seen yesterday's Edpuzzle videos, as well as what we're going to see going forward, because this is going to be all a part of your labs. Like, for example, this CVPM model, and data, your evidence, standard deviation, standard error, the equation of alignment, inclusion, percent error. So they covered all the basics. That's what we're going to do as well. So let us go forward. Standard deviation. Basically, how much standard deviation is a measurement of how much your data points deviate from the average. And the average in your case or in any case is going to be the best fit line. Why I would say the line of best fit? Because we're going to get that one data point that averages or goes through all of your data points in the best way possible. That's why we call it a best fit line. So this is best line. This is just my lay interpretation to you. Don't have to give a technical definition. We want to try and speak English as much as possible. With standard deviation, you can get the technical definition, but let's try and make sense out of everything. So the standard deviation, how much your data points deviate from the average, which is your best fit line, calculated in a standard way. And we're going to show the standard way, or a standard way. And standard is generally, it generally means in physics or science, the agreed upon way, the established way, the standard deviation. All right, so now, any questions? We've seen this already, so I'm just going to arbitrarily get some linear data, right? So let's say that in your lab, now you're going to be doing this for your data. Everybody's data is going to be different. This is just an example here. X versus T, and let's say I have 1.1 and the first second, 0, 0, that's understood. And then I go 1.3, 1.5, 3. Now, of course, in the lab, things are going to get a little wild. There's going to be a little bit of bumps on the table or the floor or something like that. Your data points might not be exactly linear, but they'll be linear enough, if you will. So I'm going to go like the next one would be 1.8. And then let's do fourth second. And then let's do 1.11. Does anybody in here, have you guys seen a bunch of 11s all the time? Like when you look at the clock, you see 11s. Like you're not looking at the clock for a long time and all of a sudden you see 11, 11. People experience that. I experience that all the time. Anyway. All right, side tangent. 1.13. And then 1.15, I'll stop at 7. How are we going to calculate standard deviation on all those data points? Make sure you have that before I go to the next. So take our data. We know that this is going to be basically linear. You can plot the points in a graph as we've done. We plotted those points and we graphed best fit line. And so now we want to do standard deviation on all those data points. X versus T, meters, seconds. So let's see. Let's see if I can just write the instructions up. So standard deviation. Anybody remember from yesterday? But if we don't, I'm just going to talk us through it. I'll have the instructions later, if not real time. Okay, everyone here got your TI 30. Hopefully most of us got TI 30 or TI 89. I think it's going to be roughly the same. Hit the second function, right? Second data. And you're going to see one var. Hit enter. Let me see if I can abridge these instructions. You're going to choose one var, meaning one variable. After you've done that, hit data and start entering those points, the points that I just put here on screen. Okay. Yeah. Well, I don't know. You can try and look. Anyway, yeah, if you have a neighbor that has a TI-30 and you don't, so just follow these instructions for right now, and let's get it cracking. So start putting your data points in. You see an X1? Show of hands. See an X1? Did you just follow the instructions so far? Anybody lost? Okay. So let's just have a seat, more of this empty seat. So for those of us who are online, all I did is just repeated what we did on Edpuzzle. Which I will just write up because I want to continue on. So 1.15. So hit stat bar. It's going to say calc or whatever. It's going to go to the next screen. It's going to calculate. The first number you see is in, and you should see 7. Anybody see that or not see it? Okay, maybe you didn't follow all the steps. I'll come over. Anybody see 7? Okay, we got your one guy. Anybody else? Okay, we got a few guys on people. All right. So that's going to be in for 7. 7. That basically means how many numbers we entered. We entered 7 numbers. You can scroll, use a scroll button. You should see an average of 1.29. So this symbol here, X bar, that is basically our slope, our best fit line that we see. The best fit line is the average, 1.29 meters per second. Right now we're just at 1.29. We have to interpret it physically. So 1.29. And then the last number on the screen, sigma, that's the thing that we use. There's 2 types of sigma. There's the S and the sigma. And that is, if you did everything correctly, your standard deviation should be 0.244. I'm just going to use the first 2. That's, you don't need. Okay. So that's how we basically do the standard deviation. So basically, again, what is standard deviation? How much do all of your data points fluctuate from this average? And when you write this stuff properly, you know, basically writing it empirically, your standard deviation result is going to be the average plus or minus 0.244. This is how you would express your data, right? Because what this means graphically is that some of your data points have deviated from the average. You're going to see this in real time. Point could be here, there, stuff like that. It could be 1 or 2 on the line. But these points are deviating. That's what's meant by standard deviation graphically and mathematically. 1.29 plus or minus 0.244. That means that all of your data points are within 0.244 of the average. That's what that basically is. Question? Oh, okay. Yep, so that's what we have. This is going to be let's see, I'm gonna write it here. Yes. Average plus or minus standard deviation. And so since we're in our CVPM and we are calculating velocity, this will be 1.29 plus or minus 0.244 meters per second. Because I hope that by now we have calculated the slope. And we got the equation of a line last time. That slope is the velocity. I'm just going to let you know right now, that slope is the velocity. This thing is sensitivity out smart one there. So when it's said in your CVPM, calculate the slope, well, obviously it's not just going to be changing y over changing x. I mean, it is essentially, but we're making new physical quantities out of the slope. So m is no longer going to be itself m. The slope is going to be what we interpret as the velocity, the average velocity. Okay, so that's going to be delta x over delta t. Rise over run. X dash minus exponential minus t initial. So how do we look at that on the graph? So x versus t, we calculate the slope. This is going to be our final position minus our initial position, which is 0. Let's say that our final position in this data, was 1.15. Our initial position is 0. Our final time, 7 seconds. Our initial time is 1. Or you can say 0. All of that. Come in and have a seat anyway. Don't have to be late. So then we just divide this. 1.15 divided by 7 gives us the velocity here. Now you're going to do that for your data points. This is just an example. Those on the internet, obviously not, I'm doing it at my smartboard. I'll try to plug this in as we go along. So as of today, most of us are here. Anyway, 1.15 divided by 7. That's 0.16. Just use the first two decimal. Don't have to get too fancy. 0.16 meters per second. Right, so again, I'm just doing that a quick example. The slope that you're going to calculate in your CVPM, if you haven't done it already, the slope that you're going to get, you translate that up to a velocity. Because we are translating, we're going from the abstract algebra quantities to real physical quantities. Velocity, system, y-axis, perfect. We've seen that already, but probably forgot. So if you haven't done that, you want to do that for your slope. And then, yes. So get your packets out. Let's do it. Has everybody done the slope? No? Yes? So make sure you have, if you haven't, make sure you do that part. I think it says on page 3, it says calculate the slope, right? So what you want to do is get that slope or that velocity really. Get the standard deviation of your data points. Okay, so today's work, we're gonna all right, make sure that on page 3 of the CVPM, slope, which is the velocity, then get the standard deviation. And so whatever the standard deviation is of your data point, put the velocity, like the example that I have, 1.29 plus minus 0.244. I want you to report the velocity this way, in this form. The velocity itself is the best fit line, which is the average slope, right? Velocity plus or minus standard deviation. That's what we're going to do today. One more thing we're going to do with our data points is calculate the standard error. Okay. So quickly, I know I've gone over my time, but hopefully we can get all this in here. So standard error, I'm just going to be very basic and upfront with you on standard error. Standard error is a check on the standard deviation. Just a check to see how credible it is. Right? So standard error, I'm going to abbreviate it as SE. And then the basic equation for that is standard deviation divided by the square root of the number of measurements. If you have your standard deviation, in this case, you have standard deviation 0.244 divided by the square root of 7. This is just my data here. Yours is going to be 5 points, 5 data points. Whatever your standard deviation is, you're going to put this down here and divide it by the square root of the number of results that you, data points that you have. Right, so it's going to be 0.244 divided by the square root of 7. I get all my parentheses, right? So we get 0.09. So that is just basically a check on the standard deviation. You could just leave, you could report the standard deviation with the standard error, with the standard deviation. It doesn't really matter. So, or just leave it as is. So this is our this was our error on the standard deviation. And if you did this correctly all the way through, your standard error will always be less than your standard deviation. Right? Okay, so that's what we have. So at the end of the day, we're going to follow the order in your CVPM, get the slope, which is your velocity, standard deviation, whatever your velocity is, plus or minus your standard deviation, and then just write up your standard error. Yes. What? A Chromebook charger? Okay. Come and grab it here. Okay. So that's it for me. Let's make sure that we get that stuff done today.